Okay, so now we start our session for nuclear energy. And I would like to invite on stage our speaker, Dr. Victor Nian. He is the Chief Executive Officer, Center for Strategic Energy and Resources. And his topic for today is a future clean energy ecosystem enabled by advanced nuclear power technologies. Please welcome Dr. Victor Nian.
Thank you, ladies and gentlemen. Thank you for the organizers for the kind invitations. This is another topic. I guess it's the second time I'm speaking in this conference about this topic. Well, usually when you hear about nuclear energy, you just think about or hear about the discussion about nuclear energy produce electricity, and then you generate electricity, you sell electricity to a market, right? But the question is, what else? If you're just trying to think about nuclear energy as a power source, then I think we are really limiting the applications. And in fact, the benefits of nuclear energy in that aspect goes far beyond just power production. Just a little bit of an advertisement for our center. So Center for Strategic Energy and Resources is a new think tank that we set up. We actually call ourselves Think and Do Tank. So there are two components to it. As a think tank, we look into policy, strategic advice to government and companies. And also we try to do what we call building consortiums of partners along value chains. For example, if it's nuclear, that means all the way go down, as I was showing the examples from, for example, downstream use case of electrification for maritime, for land transport, to the energy production options, and then all the way upstream to natural resources and also the infrastructure supply chain. And so that's what we try to do to really grow together with the value chains in the future. There are a few tracks that we're looking at today. Future energy options, so anything and everything that's got to do with energy production, be it fossil fuel, hopefully with CCS, with CCUS, nuclear energy, renewable energy, and strategic resources, for example, lithium for batteries and cobalt for that matter. Energy transition pathways is where we were looking and by and large leveraging on our Center of Excellence for energy systems analysis. So this is where we look at scenario planning in the long term, and also life cycle assessment of individual projects and also the value chain. And then that leads to what we try to build, which is smart energy ecosystem. So this is where we bring not only the competitors as our corporate members, but also companies along the same value chain that will form a complete solution to help countries, say, achieving 25% of hydrogen by 2030, for example. And we're looking into, for example, sustainable financing, and that provides our corporate members a benefits of having access to sustainable linked loans, and also we provide the analysis of what is up and coming in the market framework, for example, and also the policy and regulatory changes. Then the last bit, of course, looking at policy at the national or regional and even global level, and advise companies and governments what are the strategic options going forward. And today, we're specifically looking at nuclear energy. And this is where we're looking at the value chain of nuclear energy for the different various applications. One case study in my talk, I will talk about that. Hydrogen economy, we're working on basically mapping out what are the value chains and what are the issues, technology gaps, policy gaps in the hydrogen value chain. And we're actually working on a book for that topic. And of course, maritime decarbonization is a hot topic today. And we're looking at how nuclear energy and the other alternative marine fuels could help accelerate that journey. So, well, I guess the topic of today, I would usually, talk about nuclear energy. I would usually say that's my favorite stuff, which is the 4 phases of nuclear power plant development, which I defined in one of my papers in 2018. So, if you call it the first phase or the second phase, is basically that's where we enjoy the large-scale, first-of-a-kind nuclear power plant being demonstrated in, for example, US, Canada, UK, and also then the Soviet Union to prove that nuclear energy actually works. And then quickly went into the second phase of rapid scale up of the nth of a kind, for example, light water reactors or pressurized water reactors and several designs. Right? Until then, of course, you hear about the famous accident with 3 Mile Island, Chernobyl, and very recently Fukushima. Of course, without going into the details of what caused that, you see, over time, there has become a shift from the Western vendors, we call them, or Western front runners, to the East Asian market So that is where across the 60s and 70s, the technology transfer from US to first Japan, in South Korea, and then eventually China, also taken from France. And that's where nuclear reactor market gets developed. But of course, after Fukushima, there was a lot of debate and discussions around having passive safety, advanced safety, enhanced safety, so that you can become a Fukushima-proof kind of reactors with the generation 3 plus designs with passive safety, for example, and some of these Gen 4 designs with what we call inherent safety. So safety already built in within the physics of nuclear reactors, so you will never have a Fukushima kind of problems. And that is where we are post 2020. Right, looking at what are the in the new phase of development, what are the opportunities and challenges with this advanced nuclear power technology. Right, so what I just wanted to highlight is, okay, we have gone through these 3 or 4 phases already, and the 3rd and the 4th phase of nuclear development is almost happening in parallel. And in fact, if you're looking at timeline 2030, where we're actually expecting some of these generation 4 type of technologies, in particular, I'll be speaking about is the molten salt reactor today, is actually going to become a reality by the time frame. And of course, there you also have the other land-based options, which is not really of interest for today's topic and for this conference. But if you're interested, I can also explain about the other ones. Right. So start with the first key study that we did. So back in the year 2017, we started looking at the feasibility of integrating grid-connected battery storage. And then we decided to extend that idea a little bit further to look at cogeneration or power-to-gas options. So in that sense, we asked the nuclear power plant to follow the load in load following productions. One way is to supply electricity when you need, and also when there's excess electricity, when you don't have that much need, it is either charging the batteries or it is producing hydrogen at a time. So then the batteries can then discharge back to the grid when the price is right, or use the hydrogen as other fuel, so that you have better what we call levelized cost of energy production. And we did a comparison across different technologies. So these are floating power plant, small modular reactors, land-based, and we compared that with the generation 3 and 3 plus large reactors, which the US is looking at and basically using existing plant for hydrogen production. And to our surprise or no surprise, we actually assumed first of kind cost for the floating nuclear power plant and also the SMRs. And it turned out the levelized cost of energy production, either for load following operations or for cogeneration of hydrogen, they are not really far away from, for example, the large reactors. And of course, these costs are not exactly competitive with fossil fuel, for example, coal, but they are much more competitive as compared to natural gas with today's gas price and what is going to go forward into the future. So that's the first idea of thinking about nuclear energy beyond just power production. And then later on, we moved into a study where we're looking at maritime applications. So we started off with looking at electrification options. So, I mean, of course, we understand we can electrify the coastal vessels. They don't travel that much of distance. But what about if you were to electrify ocean-going vessels? Now, read this imagination. And if you travel from, for example, some ports from Singapore to Qatar, for example, right, you will definitely need to have some charging stations in between, just like how we do with land-based vehicles. So then we made some bold assumptions. If we have some floating power source available out there in the sea, not too far from the shore, hopefully, with floating solar, floating wind, and also floating power plant, and then coupled with something that we are already familiar with, marinized energy storage, and this is not exactly a new technology. Right? And then, of course, high power charging, this is also not a new technology, land-based. Of course, you have your own challenge with ocean-based. So assuming some of this, using a really conservative estimation of the cost, actually on the high side, we were comparing if we were to electrify a model tanker, a specialty chemical tanker, and assume some distance where you need 1 or 2 chargers on the way. And we look at what is the cost of shipping or cargo shipping with electrified ships, and compare that with a conventional ship that runs on bunker fuel. And we are surprised to find out that actually it is economically competitive. It's actually economically competitive. Right? And you might be imagining, well, these are all have its own challenges. But let's say the cost can take care of those technical challenges, and you can actually electrify them today already. And then we then go ahead and take a deeper dive to look at what are the implications, for example, if you slam the carbon tax to the maritime industry. And if you have different cost levels of bunker fuel, then it becomes more obvious that these options are going to be more cost competitive. So what we are then studying here is, well, nuclear energy is actually just part of the bigger value chain. We are not just saying that nuclear energy is there, floating nuclear power plants, you can produce power. I mean, of course, we recognize the benefit. You don't need land space. It is much safer. You have access to a large body of water. But we're thinking much more beyond just the boundary of energy production. We're thinking about, for example, if you have a floating nuclear power plant around a facility, then you would definitely have auxiliary services, backup systems, battery rack in this case, charging systems. And then you also have the use case, which is having electrified vessels. Right? So with one option, you're actually enabling multiple options and multiple choice opportunities of innovation and technology development down the value chain. Right? And if you think about maritime decarbonization, and this probably is one of the value chain of grouping that can really bring credible offers, rather than saying, I have a floating nuclear power plant, I have a charger, right? I have a battery storage. I mean, the value proposition of that, this complete ecosystem will be much greater than just add up the individual ones. So what do we mean about nuclear ecosystem? So I believe we're mostly engineers, so we understand a bit of thermodynamics. So imagine if you're working with a high temperature heat source, 700 or 800 degrees, for example. As you produce energy at that level of temperature, you could do, for example, high temperature electrolysis. Maybe not enough for hydrogen thermal decomposition, but you can do high temperature electrolysis. Temperature goes down a little bit. Maybe you can do for ammonia production, then maybe for methanol production. And after that, you do electricity generation and the waste heat, then use for example, water desalination. And then imagine that all floating somewhere in the middle of the ocean, not occupying any territorial sea. This is where we call it a floating multi-utility complex, producing multiple commodities, competing in different markets. And that means it will be different revenue streams for whoever is in that ecosystem. And that in itself already has downstream use cases. For example, refueling for ammonia bunkers, to electrify and charge whatever vessels that you might have near coastal or ocean going. Right? And you can also produce electricity to onshore facilities. So imagine a country, for example, the Philippines or Vietnam, where the load might not be as high as what we normally expect. And depending on the shape of the loading, depending on the shape of their load curve over 24 hours, you might have multiple opportunities for other commodity productions in that place. Right? And if you're able to sell enough hydrogen or ammonia from this facility, then maybe Philippines can enjoy really cheap electricity from the floating nuclear power plant. So what are we saying here? So yeah, I guess I already covered that, right? So basically, an ecosystem approach is saying that you start from the downstream use case scenario. In this case, we're looking at what can you apply, what can you use from the various commodity produced. And then we look at what is the infrastructure. So in this case, floating structures, and we have all the experts in the room that can design and build floating infrastructures. And we are looking at safe. So those are the keywords: safe, clean, affordable. And that's important. I mean, if you have a beautiful, really nice power source, but it's just expensive, it's not going to work. And it has to be safe, especially in the context of nuclear. And it has to be clean by means of allowing nuclear energy to enter into the green taxonomy. So that, well, this is probably something that we considered for ESG finance, for example, and consortiums of companies. So in this case, I believe you can already see this will be a huge team of different companies. Even if you look within Singapore, there are companies that can be part of the ecosystem already today. And then of course, policy and regulatory frameworks, these are the most important things. I mean, of course, as of today, if you look at the IMO regulation, the International Maritime Organization's regulations, and you look at the International Atomic Energy Agency's regulations, well, you will see the two are not really talking as much as we want them to. Right? So one regulation might be a barrier for another one, and vice versa. So in order for us to really have some kind of floating solutions out in the sea enabled by nuclear power plant, there is a need for regulation and policy to change at the international level. And of course, depending on what the national or judicious law is, you might actually have some freedom to accommodate floating nuclear power plant today, some part of the world. And yeah, so this is actually another angle that we're looking at for Singapore, is to look at if Singapore as a small country, or rather as an example country, small city state, were to participate in the nuclear value chain, what are the strategic considerations where Singapore can play a role in it? And also map out Singapore as a newcomer, as an example, a newcomer country, what it needs to be done in order for us to go from zero to having a business case for nuclear energy. And yeah, thank you very much. That's my presentation.
Thank you so much, Dr. Victor Nian, for delivering the speech. So our next speaker is Dr. Giulio Gennaro. He will be connected with us through online, and he's the Chief Technical Officer from Core Power. Is Mr. Giulio online?
Hello?
Hi, yes, Mr. Giulio. So please welcome Dr. Giulio Gennaro, and his topic is Advanced Nuclear for Sustainable Power at Sea. Please welcome.
Good evening, everybody. I'm Giulio Gennaro. I'm the Chief Technical Officer of Core Power. We were based in Singapore until 2020, and now we are based in London. We have started this journey in 2018. Actually, we have been considering this possibility earlier, but we were incorporated in late 2018, and initially with the idea of using nuclear power to decarbonize shipping, and now understanding that there is a whole marine ecosystem that can be decarbonized and not just shipping. Okay, so today we are a company with 14 team members, 4 board members, several advisors, many expert consultants, including Ivan Stoichev, that is a member of IMarEST, and we are 42 shareholders, which are mainly ship owners, and the ship owners control more than 2,000 ships, large seagoing ships worldwide. Now, our mission is to co-develop and finance advanced reactor for marine and industrial application, to create new market for this really true emission technology, engineer a nuclear electric power package, and we will speak about that later, lead the modernization of marine and nuclear regulations, and also to build the ecosystem need to train and to manage, train the crew and to manage these systems. Now, we all know about shipping emissions, but the important thing that needs to be highlighted is that if we look into IMO greenhouse gases 2018 report, we notice that the largest 20% of the ships are responsible for about 80% of the emissions. And the largest 10% of the ships are responsible for about 50% of the shipping emissions. That means that if we want to decarbonize shipping, we need to tackle the biggest ship, which are the hardest to be decarbonized. And this is where nuclear comes into the picture. If we consider the nuclear industry and the marine industry, we see that there is an inevitable connection between the two. Nuclear as a really true emission technology, but nuclear industry needs a mass market. Nuclear industry has been focusing on very large grid scale projects, and instead it should shift its focus to small and medium projects at sea, shifting also its view from these big projects to products. While marine is a mass market that it's in need of a real true emission technology, but has also the means to finance and to order large numbers of these reactors. Now, if we look at the past, we have seen that transformation in shipping happened because there were gains, there were competitive advantages to be gained in moving from sail to steam and from steam to diesel engines. Now, if a new revolution in shipping has to take place, it cannot take place because of, let's say, external forces. It will take place only because there are internal forces in shipping that realize that a new competitive advantage can be gained for this technology, and this transformation can be monetized. Now, if we consider advanced nuclear, we see that it's a truly disruptive technology with superior economics. But in order to make it really superior and available, we need mass manufacturing and standardization. Now, not all nuclear technologies are, let's say, compatible with the need of marine deployment and in particular of shipping. There are three key criteria that we believe are fundamental. The first criteria is that we need technologies with exceptional long fuel cycle, because we don't want to open and close the reactor every so often to refuel it, to remove, let's say, fission byproducts. And this is needed because we don't want to handle fresh or spent nuclear fuel on board or in port. Okay, so this is mainly to mitigate proliferation risk, which is one of the biggest concerns of the regulators. A second key criteria is basically constraint. We need the reactor to be of modular construction, that must be we must be able to mass produce it, and must be relatively small to fit on board the vessel and affordable. And then there is the key, really key and most important criteria. We need a very small emergency planning zone. Every reactor has an emergency planning zone that needs to be kept safe in case something goes wrong. For large pressurized reactors like PWR that are used for, let's say, grid scale power generation plant, this emergency planning zone can have a radius of tens of kilometers. If we use small pressurized reactors, the emergency planning zone shrink, but it's still quite large, can be several kilometers. We need the emergency planning zone to be as small as possible, to be confined to the hull of the vessel, so that there is no encroaching between the vessel, the nuclear vessel itself, and the external environment, the piers, the quays, the terminals, the ports where the ship operated, the confined, restricted waters where the ship will be traveling. And these can be achieved only with a non-pressurized core, a core that operates at ambient pressure. The difference, and excuse me for the, let's say, very layman comparison, is between a pressure cooker and a saucepan. In a pressure cooker, we have pressure. If the pressure cooker explodes, it is not an atomic pressure explosion, it's a mechanical explosion, but the material that is inside the pressure cooker gets thrown around, and we have a large contamination area. If we consider instead a saucepan on top of the stove, if the saucepan breaks, we have a leakage on top of the stove, but we don't have missiles projected around the stove. So we have a very small contaminated area. Actually, we move from kilometers to meters. Okay, so this is why we need unpressurized core, to be able to keep the emergency planning zone inside the hull of the vessel, avoiding any contamination to the environment and any exposure of the crew and of the general public, also in case of an accident. Okay, so this is what I was saying before. You need to consider, for instance, a container ship berthing in Tuas Megaport, and we need to be sure that the emergency planning zone is inside the hull of the vessel. Now, the technology that we have identified for large ships is molten chloride fast reactor. A demonstrator will be available post-2026. There is an exceptional fuel efficiency. Basically, this technology needs 1 gram to produce megawatt power per day. If you consider with slow speed diesel running on heavy fuel oil, 1 megawatt per day requires about 4 tons of fuel. And as far as CO2, you will have about 3 times as much. This is a compact modular design that can produce about 180 megawatt thermal, so more than enough for the largest majority of the ships. And again, it is ambient pressure only. We are cooperating on this technology together with TerraPower, the reactor design company funded by Bill Gates in early 2000, with Orano, the nuclear French fuel manufacturer, and a Southern company, one of the largest utilities in the United States, already managing a fleet of pressurized water reactors. We were awarded around $150 million by the US Department of Energy under the Advanced Reactor Demonstration Program on an 80-20 cost share basis. It is important to underline that these technologies need substantial private investment. It cannot only be governmental investment. The funding is for the proof of concept, the molten chloride reactor experiment, which will be fully tested by the end of 2025. Another technology, slightly different, that we have also identified is the Vinci microreactor. This is a solid state reactor, which is very compact, but also low power. So it's about 15 megawatt thermal and about 5 megawatt electric. We are cooperating on this with Westinghouse, possibly, let's say, the oldest and most, let's say, well-known nuclear reactor designer and manufacturing company. We are entering a 5-year development program. The prior licensing of this technology has already been launched, and already substantial grants have been given to this technology by both the US and the Canadian government. Now, talking about ships, what are we envisioning? We are envisioning nuclear electric propulsion. The reactor will produce heat. There will be a power conversion system that could be a steam system or could be a supercritical CO2 system, converting heat into mechanical and then to electric power. And this electric power will be distributed on board to all the different users, including propulsion motors. And this will also allow to use, let's say, a diversified propulsive arrangement. And we will not be restricted to using, let's say, single screw ships. We could go multi-screw, or like you see in this picture, we have a contra-rotating podded arrangement. There are a lot of advanced propulsion arrangements that could be easily integrated. Now, let us consider container ships. Container ships are currently designed for around 20-22 knots, but are operated around 15-18 knots. Now, things might be different due to the, let's say, very high rates that they are, let's say, freight rates that the vessel are, let's say, getting nowadays. But this was the trend. And we need to remember that before 2008, the design speed of this ship were 25, 26 knots. Okay, so now what have we been doing? We have been trading, let's say, lower speed to reduce fuel consumption, but we have lost capacity. So these ships have large fuel consumption, also at relatively low speed, large emissions. And with conventional ships, we see that large ships, very large ships, are profitable, but they are not flexible. But if we look into smaller ships to gain flexibility, we see that they are not profitable. The margin per TEU fall drastically. Now, if we consider atomic ship running on marine molten salt reactor, we could go back to the speed that we were using to design in 2008, so 25, 26, even 30 knot. And there will be no need for slow steaming. Basically, the ships will be operated very close or at design point through zero emission ships. Of course, economies of scale will still be there. So large ships will be more profitable than smaller ships and much more profitable than conventional powered vessels. But small ships will be back into the game because they will be flexible and profitable, contrary to now. Now, another case, an ore carrier trading between Brazil and Indonesia on a 60 days round trip. If we consider this vessel running on low sulfur heavy fuel oil, per round trip, this vessel would consume about 3,700 tons of low sulfur heavy fuel oil, emitting about 11,000 tons of CO2. And the cost of the fuel nowadays, probably, well, more than that, but let's say $700 per ton plus carbon tax. So altogether, let's say, looking at the EU, let's say, emission trading scheme, there would be about $1,000 per ton. If we consider running the vessel on green ammonia, the fuel consumption per round trip will increase to 8,800 tons of green ammonia. And it must be green, otherwise there will be basically no meaning, no real abatement. Now, of course, the CO2 emissions will be very low. The total life cycle emissions will also be low. But now the cost of the fuel will be 3 times to 6 times higher than the cost of fossil fuel. So the economics will be destroyed. If we consider these ships running on a marine molten salt reactor, the fuel consumption for round trip will be 1.1 kilo. I repeat, 1.1 kilo. So basically, the stability at the departure and stability at arrival will be exactly the same. This will also be the technology with the lowest total life cycle emissions. And over the course of the life of the vessel, which for a nuclear ship, we estimate in 30 years, there will be a savings in total life cycle cost of about $450 million. Now, another case, LNG tankers. So let's consider a 150,000 cubic meter LNG tanker. Suppose to compare operating this vessel at 20 knots against a conventional vessel operating at 20 knots. So the total life cycle savings will be about $1.5 billion over a 30-year life. There will be a saving in CO2 emissions of about 4.3 million tons, and there will be increase in carrying capacity of about 6.5%. Instead, the increasing capacity is because the system, the nuclear system, is much more compact, okay, both in weight and volume. Instead, if we consider the vessel compared to a conventional ship operated at 16 knots, the savings will be slightly less, $1.3 billion US savings. The reduction in CO2 emissions will be also a little bit less, about 3.2 million ton savings. But now, due to the difference in speed, the vessel will have a 27% increase in carrying capacity. And the nuclear ships will be able to fully reliquefy the product. So, in the end, atomic will make ocean transportation extremely competitive, real zero emissions, higher profit, no need for slow steaming, and extremely important, no fuel cost volatility. Of course, there is a catch. The catch is that this is a high capex, very low opex type of business. So no ship owner would, let's say, enter an agreement, would want to buy a nuclear reactor because of the financial risk involved. So what we need is a new business model in which there is a long-term power purchase agreement, a long-term lease of the reactor, similar to what is happening nowadays in civil aviation, in which the engines are not sold, but basically the manufacturer is responsible for the true life maintenance of the engine. The advantage of this new business model is that the ship owners will not be responsible to the operation of the nuclear reactor. They will not be responsible to the commissioning and disposal of the nuclear reactor, but the manufacturer of the reactor would still be responsible for the true life and for the end life of the reactor, sparing the ship owners a lot of headaches. And what about the waste? So this is, I mean, the elephant in the room, okay? Now, suppose that we have ultra-large container ships trading for 30 years at 30 knots, so a huge power of such speed. The total life cycle fuel, which means high-level waste, that will be created by these ships, it will be, let's say, 1.8 tons, about 0.6 cubic meter high-level radioactive waste for a ship. So basically, a small fridge of a ship that is carrying, let's say, 20,000 containers for 30 years. Okay, so the waste is actually more an emotional, let's say, issue than a real issue. Okay, and again, there will be a lot of good in this waste. Okay, we could extract, for instance, medical radioisotope from the waste, which will create an additional, let's say, value out of it. And again, what is extremely important in any case is that nuclear waste is not delivered to humans or the environment. So nuclear waste is extremely well managed, and it is, and it will be extremely well managed, unlike, let's say, chemical waste or other waste that all industry produce. But this technology is not only a technology that is, let's say, of interest for shipping. We believe that this technology is of extreme interest for all marine applications. We have seen that offshore oil and gas industry has proved us that offshore is faster, safer, and cheaper than deploying it on land. So we can use the same concept to create floating nuclear plants. Okay, they are a mature technology. In this case, we have a 7 hull type floating plant. We can mass manufacture it in large series in shipyards and deploy it around the world. So with a massive, let's say, reduction in cost in comparison to land-based plants, being a lot safer, both because it will be farther away from inhabited settlements, and also because the real big problem of a nuclear plant is access to a cooling medium. But if we are at sea, we have basically an infinite cooling medium at our disposal. We believe that this will be the future of nuclear energy power generation.
Yeah, sorry for interrupting. We are almost running out of time.
I'm almost finished. I will rush through. So we believe several let's say applications will be possible. So power to shore, generating at sea for the grid, water desalination, and of course production of green electrofuel like hydrogen, ammonia, or methanol, or green methanol at the point of consumption. Okay, so for instance, in Singapore is selling around 50 million tons of heavy fuel oil equivalent. We could produce this green electrofuel in close to Singapore, and not having to transport them from all the world to Singapore. So this is an idea. So we have a floating power plant producing power, an FPSO converting this power and seawater and nitrogen into green ammonia, which would be then dispatched to port. Of course, there is a lot of regulatory work to be doing, and we are working with the International Atomic Energy Agency and with the IMO, and with flag states. We are very close to the UK and the US flag, and we are also getting more and more, let's say, foothold in Japan. We are also members of the World Nuclear Transport Institute, through which we have observatory status both at the International Atomic Energy Agency and IMO. We are now launching a client program. There will be a webinar on 13th of July, and you are invited to check our, let's say, website and subscribe. And we will arrange an in-person event in Asia in early 2023. And the object of this client program is to, let's say, learn altogether about how to manage nuclear at sea, perform technical economical evaluations of, in particular, of ship application, and to do concept design together with our client, and also to consult with them on interim measures. Please free to reach us for any question, and please subscribe on our web page for update.
Okay, yeah. Thank you so much, Dr. Giulio, for his wonderful speech.
My pleasure.
So now, please welcome our next speaker. He is Professor Lim Soon Heng. He's the advisor and founding president Society of Floating Solutions, Singapore. He will be sharing his topic, nuclear power plants, safe and necessary. Please welcome Professor Lim.
Thank you very much. Correction, I'm not a professor. I don't know where this professor came about. Okay, first I want to thank the two preceding speakers before me, because they have laid the groundwork for what I'm going to say about floating nuclear plants. This talk I'm going to base on this state, much of it has already been discussed, about the sea and why it is necessary. Why Singapore must, I say must, not should, transition to nuclear. How it can be done safely. First, I think we know all that's happening in the Ukraine. Right? War in Ukraine is actually a war between the US and Russia. With Ukraine as the proxy. And many countries in Europe and around the world are collateral damage in this war. Right? Principally, it's Germany. Germany is suffering the most in this war because they made a mistake after Fukushima to remove all the, not all, but many of the nuclear power plants, right? And swap to wind and solar. Now they are paying the price. France, on the other hand, is laughing all the way to the bank because they are 70 to 80% nuclear-based economy, right? The next question is, what about Ukraine? Are they going to be in danger? Ukraine depends on nuclear for most of its energy needs. You would wonder, are they going to be in danger with all these nuclear plants and with Russia bombing away? The answer is no. The Russians are bombing all the oil storage plants, oil storage, and all the thermal power plants. And they have until today not touched the nuclear plant for very good reason. Right? The Chernobyl, we know what will happen. So, and then look at Japan. Japan is also another country that is suffering collateral damage. Just recently, a few weeks ago, the Japanese said, let's go back to nuclear. Forget about Fukushima. Let's go back to nuclear. Right? 80% of the Japanese firm wants nuclear power. What about Singapore? We too are suffering quite a bit. It's not as bad as Germany. But there is this real risk. And that's why I'm so passionate about this business of nuclear for Singapore. 80 or 90% of all our energy needs is in the form of natural gas, which is coming from this place called West in Indonesia. And the South China Sea, as you know, has a lot of contention. Right? The dotted line is 9-dash line. Right? And China is already telling Indonesia, no more drilling in Natuna. Right? So what could possibly happen if we lose that source in Natuna? There'll be no lights, there'll be no transportation system, everything that you take for granted will disappear with damage to that pipeline. But apart from military conflict, that pipeline is also taking a risk in disruption of your energy supply. Any of these things can happen. Agreement between Singapore and Indonesia, terrorism, including cyber, seizures of the gas field by China or by whoever, right? From mismanagement and maybe depletion of gas. So our dependence on gas to the extent of 95% is really making us very vulnerable. Very. we need to do something about it. All these years we've been burying our head in the sand. Time to wake up. Now, one way, of course, to get over this problem is to be able to have what is called strategic reserve. That means if your supply line is interrupted, you can depend on whatever reserve you have to keep on going. Right? But the problem with gas and even oil is that it takes a lot of space, a lot of land to store enough energy to last you 2 weeks, 2 months. With uranium, because of the high energy density, you can keep all the energy that you need to run all the power stations in Singapore, right? You keep all that uranium in a standard shipping container. About 300 tons. That's enough to give you 53 terawatt hours, which is the amount that Singapore is consuming per year. If we have that, the 2 boxes can run for 2 years. Right? So we need to make that transition. Otherwise, now, there are 4 options for locating nuclear power plants: over land, underground, on the sea, under the sea. Yes, under the sea. Right? And let's see. I just want to run this quickly over because there are some professors in the university who are promoting this idea of building nuclear power stations underground. The reason why I'm not going for that is that possibility of a meltdown is pretty high underground. And you have to transport uranium, unload it at the port and transport it inland. Whenever you have to transport uranium through the city, that's a risk. And then it's not easy to scale up or to scale down, and difficult to decommission. So we might as well forget. Showing you. Anyway, what is missing? One stays there, the island of Singapore. Right. Right? Yeah. Okay, I'll just let the white space there. Actually, I got an image of the island of Singapore. Right? It stretches from here to that side. And this red dot here are what I want to show in relation to the size of the Singapore island. Right? Because people are saying, where can you find the space in the sea to put all these things? It's actually very small. And I'll go into detail. Right? The other thing about nuclear plants is that we don't want to go into the gigawatt plant. Right? So we want to stay small. Small is safer. having a gigawatt plant is a lot more dangerous than having a small nuclear plant. Okay. Okay, I just want to touch on this. What evidence is there that nuclear power is safe? The reasons for nuclear power being safe is already been talked about. What I want to show you here is the evidence that it is safe. The number of people who died per 1,000 terawatt hours in 2012 due to natural gas generation is 4,000, right? Hydro 1,004 and rooftop solar is 140, but with nuclear it's only 90, right? And these are statistics gathered in Google them, right? Fukushima, how many people died as a result of radioactive exposure? 1. Right? Chernobyl, how many civilians died? So that's the evidence of nuclear power exposure risk. Since 1970s, early 1970s, there have been at least 20,000 shipments of uranium, measuring 80,000 tons. There has not been a single incident of mortality as a result of this. As Dr. Nian has already mentioned, today all the nuclear plants are addressing this problem of backfire. Passive cooling is a feature. With passive cooling, you won't have a lot. So it's pretty safe. And this is what I think we should develop in future. The idea here is to have nuclear power plants using SMR, small modular reactors, right? And in an enclosure using either concrete or, well, I think only concrete will work in this case, surrounding it. That lagoon there, this artificial lagoon, would be about 1 kilometer in diameter. Within this lagoon, you could have up to 3 SMR reactors together with the turbine hall and the transmission equipment. Right? So here, those things in the center, that's roughly the size of the reactors and the turbine hall and the transmission system. Right? And because your load demand over a 24-hour period is not going to be constant, at night time you probably have a lower demand. So you could use that fluctuation in demand to power a desalination plant, right? And whatever desalination water that is desalinated, you could retain it in that lagoon, which is roughly about 20 million cubic meters, right? You could also take the fan fuel within that area and the new fuels too, right? You could also generate green hydrogen, either directly with seawater, which is now possible, or using the desalinated water, which is a common thing. what I want to show you is the installation of this small nuclear reactors using a floating crane, lowering into the concrete buoyancy tank. Right. So the installation is quite simple. You get the reactor onto the barge, enter it through the gate that is part of the structure, the lagoon structure, and with a floating crane, you just simply lower the SMR. In this mode, in this mode, you can see. Okay, here was the island Singapore, and that in relation to that side is the lagoon that we're talking about. So it's too small, right? So if you want to do half of the power requirements in Singapore with nuclear, you probably need 6, 7 of this, and it can be easily accommodated within our territorial waters. One. Next slide, next one. Okay, okay, I just want to, no, that one. This one, yeah, 14, yeah. Just want to give you an idea of what I was talking about the zone that surrounds that makes up the lagoon will look something like that. And this is already been fabricated in Jurong, right, to build that mega port. The same kind of structure can be used to form the lagoon. And the gate that I showed in the diagram is basically a floating gate. You want to bring some big stuff in, you just float it out, let this big stuff float in, and then you put the gate back. And to store the spent fuel, you can put it in something like this. Waste fuel or cask. Right? So the components necessary to handle that are already existing. Right? Here is how you do the storage. You got a turbine hall, and then the SMR is lowered into the floating structure using a floating crane. Right? So we don't need a lot. If it was on land, you couldn't do this. Right? And your floating workshop, if you have to do a maintenance or in the industry, they call it a scram or emergency shutdown, right? You can do the repairs on the floating workshop. Here's an example of how the SMR can be listed in. Right? This crane is actually in Singapore, and the man in charge is somewhere there. Just there he is. He's the big boss of this Asian facility. Right? Next slide. Okay. This is an example of the small floating nuclear plant. It was designed by or conceived by MIT professor Giulio, and here is that SMR, right? The rest of it is turbine hall, the transmission system. So it is pretty small, and that SMR, probably about 500 tons, can be easily transported from wherever, North Korea, South Korea, or France, or somewhere, on a structure like this, marine transport. Okay, how do we ensure safety? Because this thing is nuclear, right? You don't want it to be become a target for terrorists. So with this being in the sea, it's much easier to keep it under active surveillance than if it was on land or underground. Because once in the open sea, you have You can use long-range radar to detect any intrusion. You can also use drones, right? And the big concrete barrier is enough of a protection against collision by ships that are running off course. Right? So these are considerations that you can put in place to make it safe. And as for wind, wave, earthquake, that's not a problem. At least not in Singapore. Also, that with 3 reactors, you have sufficient redundancy so that you can shut down one and keep the other 2 going. Right? It also is a means of scaling up incrementally. So you don't have to invest in 3 reactors at one time, then do 1, 2, and then 3. So that cuts down the financing cost. What just occurred to me when I was preparing the slide, maybe it's time for all those who are involved in floating nuclear plants to form an association of floating nuclear power plants. Why does it work? It works because floating nuclear power plant is a transboundary kind of business. Right? You can build it in France, you can build it in South Korea, and the end user could be somewhere else. Right? So it can be a joint effort by core other producers like Scale and all. And it should be a joint global effort to promote this. It is also in humanity's interest because it's a clean power, right? It addresses issues on global warming, climate change. So there might be a good reason to form an association of that nature. Next one, please. Okay, here's the bottom line. Bottom line, as I say, it's absolutely necessary if Singapore is going to be resilient against disruption of supply chains of energy. The only safe way to have a nuclear plant in Singapore by having it afloat, not on land, not underground, but afloat. Right? Thank you.
Okay, thank you so much, Mr. Lim Soon Heng, to share his insight about the nuclear power plant safe and necessary. Mr. Lee, could you please stay on the stage and take a seat? Thank you. So now we are going to the panel discussion for session 4, nuclear energy. We would like to cordially invite Mr. Mike Ward, Chairman, the Joint Branch of RENA and IMarEST Singapore, to moderate the panel discussion. Please welcome. And I would like to invite the speakers to join the panel session. Please welcome Dr. Victor Nian and Dr. Giulio. Is Dr. Giulio on? Okay, yeah. And also, yeah, so please take a seat.
Right there.
Hello.
Hi, Giulio.
Hello.
Hey. Okay. Thank you all for very good talks on nuclear, which gave us all a very good view of the different areas of nuclear. There's been quite a lot of questions there, and what I'll do is try to run through some of them and figure out our way through as we go. So one question, I'll start with you, Victor, is where do you see the main barriers to implementation of floating nuclear technologies in Southeast Asia in particular, and taking into consideration
what Mr. Lim's comment on, especially with Singapore having a requirement and a threat of the potential gas shortage?
Yeah, that's a very good question. I think the main barriers I probably explained a little bit in my talk. The two aspects. One is the appropriate technology has to be ready, and by the definition of appropriateness, is not about the best. I mean, the state-of-the-art technology or the most advanced technologies, the technology that the countries think that are most appropriate for their circumstances. That needs to be there. So that means the political acceptance, public acceptance needs to be there. So that's really the first layer of barrier when you talk about deployment for judicious or national use in national territorial waters. The next layer of barriers would be from the international regulations. So, of course, now we're talking about harmonizations in the sense that there's a harmonization of designs and standardization, licensing approval for SMRs, and also we're trying to innovate, make the IMO, IEA talk together so that the nuclear regulations and the maritime regulations can go hand in hand. But as it is today, there is still some barriers. But I wouldn't really say that there are barriers, but they're just difficulties that needs to be overcome in order for a floating barge or nuclear power plant to satisfy both requirements on both sides. So that is not easy. Still, there's ongoing discussions, studies, and all that. But I mean, if you ask me today, then these are the barriers that need to be addressed. And of course, I think there's also the issue that Mr. Lim addressed about refueling, financing, maintenance, and servicing, right? I mean, Singapore being a port country, we also want to think about whether we can actually service those barges and floating nuclear power plant with whatever capacity that we already have. So should that become an opportunity and also barrier in itself? I think it's also a question.
You're saying Singapore would be potentially in a good strategic position for serving this kind of technology in the whole Southeast area and Southeast Asia area. Yes,
I mean this is what I mean by being a part of the value chain for floating nuclear power plant.
Okay, Giulio, this question I think is for you. You have your intention is to do the proof of concept by 2025. But where do you see the next steps, and how do you see the training of people that would be required to fall in with this?
Thank you. So the proof of concept will be a very small molten salt reactor, actually almost like a zero power, that will be needed to test, let's say, the neutronics. And after that, there will be a full-scale demonstrator. We intend building a marine reactor as a full-scale demonstrator, which will, of course, be first of all will be tested on land, possibly at Idaho Nuclear Laboratory in the U.S. with the support of the U.S. Department of Energy, and then it will be tested most likely on floating, like on a barge, rather than on, let's say, a full, let's say, seagoing ship. This is for a molten salt reactor. For the eVinci, for the micro reactor, possibly we would go directly. We don't need to do through a proof of concept, and mostly we will go directly to a full-scale demonstrator. And also, we believe that in this case, the first application will be a floating, like a barge or a small, let's say, ship in U.S. domestic water, because this is, let's say, our U.S. technologies to begin with.
And what the people who would man this, how would we?
Yes, so we believe that there will be, let's say, the operator of the reactor will be, let's say, licensed, similar to what happens today in civil aviation. So you have a pilot that are certified for, let's say, specific reactors. So these we need to implement, let's say, training centers in which you have, let's say, theoretical and practical knowledge on mock-up reactor, on a simulator, basically, and then on a land-based, let's say, plant. Okay. So this is part of, let's say, of this continuous, let's say, development that we are, let's say, fostering, because it's not just the technology, it's the entire ecosystem that needs to be developed. So the regulatory ecosystem, now the International Atomic Energy Agency is trying to, let's say, understand how to regulate, let's say, floating power plants, transportable nuclear power plants. So, and of course, I mean, the marine aspect of this is extremely important. Then there is, let's say, as we were mentioning, the training of the operators. And a lot of these things are already, let's say, outlined in regulation A491, which is the current IMO code for nuclear cargo ships, which is, let's say, outdated and not applicable, also because it does not follow the current safety standard for, let's say, nuclear power plants, but it already, let's say, outlines all the key issues that need to be tackled. So that's a very interesting, let's say, a document for everybody to read.
Okay, so essentially there's still like some updating to be done of regulations in order for us to be able to take those steps towards that. Mr. Lim, I'd like to ask you with regards to your concept for the nuclear reactors offshore. Where do you think the safe distance would be for that, and also do you believe that Singapore, the Singapore government would have an appetite for this, and that will go also to Victor afterwards as well?
Okay, on this question of whether the Singapore government has the appetite for this, if you ask me this question 1 year ago or even 6 months ago, I would say no. But just in recent months, you find that a number of politicians are now coming up, and the Straits Times are talking about nuclear energy. Although they haven't talked about floating nuclear energy, they are talking about nuclear energy. So yes, I think the Ukrainian war is a wake-up call. And what we're trying to do is to make people understand, especially the politicians, that nuclear is quite safe. In fact, very safe. As I showed in those figures there, number of mortality is the lowest among all the renewable energy, right? Sorry, second part of the question was?
With regards to the actual distance that
Okay.
you would put a station.
Okay, if you put a nuclear power plant on land, the exclusion zone is at least 20 kilometers, right? But if you put it in a concept like mine, right, it's in the water, right, with these barriers against the ships lighting it, you really don't need more than 500 meters radius, because if anything goes wrong, which I don't think it will, because of this passive cooling, it will not have a meltdown. If something goes wrong, you can always turn off open up the hatch, flood the whole thing, and it's all underwater, right? So your exclusion zone can be minimum 500 meters, or to be safe, 1 kilometer. And with this, much easier to convince the government as well as the neighbors that such a system is definitely safer than putting a nuclear plant on Singapore Island. Because if a nuclear plant on the island goes bang, the whole Baru and Jakarta and everywhere else is going to be affected, right? But with one in the sea, you just, flood the buoyancy tank, and you're okay.
I think some of that would be down to some very good PR with the local population in Singapore. So it's about, as you said before, Victor, it's about one of the barriers being the perception to it. Dr. Giulio, this question's for you. Whether you could comment on the potential risk of the dilution in safety standards if we were to scale up nuclear technologies in the very diverse ecosystem of shipbuilding.
Well, that's an interesting question. I think that shipping is an over-regulated industry in comparison to many others, and also nuclear is hampered by an extreme, I would say, over-regulation. Actually, one of the problems of the increasing, escalating cost in nuclear was to look for, let's say, an ever-increasing safety, even if the marginal gains are limited, while the increasing marginal costs are extremely high. So the new, let's say, the new technologies coming into nuclear, especially, let's say, molten salt, are more, let's say, related to chemical industry rather than nuclear industry. The fact that we have unpressurized core limit the severity of the accident by it's a great mitigating factor, and at the same time the different technologies and the physics also limit the likelihood of accident, which are already extremely low. So you will never hear me say that a pressurized water reactor is not safe. Actually, it's extremely safe. Okay, so I don't think that there is a risk in diluting or in watering down, let's say, the safety regulations. We need to be practical about safety regulations, and we need to understand that there is, infinite safety is impossible. Okay, regulations need to scale with the risk and with, let's say, the experience and the capability of managing. And the nuclear industry has shown that they can manage. What about shipping? Is shipping able to manage? We believe that for some technologies, it would be a problem, like a pressurized water reactor in a ship is okay for a naval ship with a very well-trained crew that is able, let's say, to keep up with the daily need of that type of reactor. But that would not be okay for a conventional, for a commercial ship. With a molten salt reactor, the need for the crew to cater for the reactor needs are very little. And so this is a feasible technology, and I don't believe that there will be a risk in watering down, let's say, safety regulations.
Yeah, maybe just to add on to that, and if you read about the UK implementation of the SOLAS Chapter 8, so United Kingdom is trying to regulate merchant ships under the UK's flag state. So that is also a way of enhancing regulatory requirement for nuclear merchant ships. Of course, that's for nuclear propulsion, not so much floating nuclear power plant. But this if this is the right addition to say, there's only going to be more regulations, which I'm kind of not really thorough. And of course, nuclear safety, maritime safety, these are the different layers of regulatory framework that any floating nuclear plant or a nuclear merchant ship needs to be in compliance with.
There's a couple of things I'd like to touch on, and it's covered in some of the questions here. One of them is about waste management. What's the cost of waste management, and what's the best ways of doing it? We saw, I think, in a few presentations that I think in Mr. Lim's presentation we were storing waste in the cask, and in the core power, I think we had the 1.8 kilograms.
1.8 tons for, let's say, 150 megawatt electric propulsion plant. Yeah. So a huge, let's say, vessel going very fast.
Yeah. So when we're looking at that waste management, how do we deal with that, and how do we scale that, and what kind of costs are we looking at?
Well, cost first. So just to give you the order of magnitude difference between geological storage of CO2, when we talk about CCS these days, and compare that with the radiological waste or high-level waste storage cost. Every ton of CO2 you pump underground is about €1 to €6 per ton these days, 1 to 6 plus minus US dollars per ton. Whereas on the high-level waste, the number is absolutely high. You're talking about $440,000 per ton. And you would imagine that this is crazy, never going to be economical. Whereas, at least in our studies, when we put that into the levelized cost of energy calculations, you don't even see the impact of waste storage costs in nuclear energy. In fact, they're still so much more competitive than you would do through a cheap coal-fired power plant with CO2 storage. And you would think that CO2 storage is so cheap, $7 per ton, but the order of magnitude changes when you look at the amount of CO2 that you need to pump underground and to find the appropriate depleted oil fuels and the right precision reservoir for your CO2. So that completely changed the whole landscape. How scalable? If you look at where the US put their waste, they never really sealed it off. So they are not strictly speaking waste. If the technology is right, you can reprocess them, and there's additional juice in the waste or in the spent fuel that can produce more power. And I'm sure that Mr. Lim will also add on about the technical part, but just last bit, I want to say that you don't need to scale up nuclear waste storage. There are not that many. In fact, you would imagine, you would read in the Greenpeace media and say there's this whole mountain of nuclear waste, whereas if you go into the mountain, you only see a few bottles of nuclear waste lying around.
If you go to a nuclear power plant, France or even the US, all the waste, most of the waste are kept in a cooling pond. That is probably the size of this room, right? And after 20 years, they're still there, right? And I read somewhere that if you collect all the waste that is nuclear waste, spent fuel, since day one, it won't cover 2 or 3 football fields. Is that correct?
Yeah.
So we are talking here about a very dense material, right? Compared with coal, mountains of ash, compared with oil or gas, the amount of CO2 there. Even if you condense it, that CO2 is going to be more than. So you've got to have a sense of the volume when you talk about the risk. Right? When the volume is very small, it's easy to keep them safe. But when the volume goes into the millions of cubic meters, it is difficult to manage that kind of risk.
So I'm going to put this one to all of the speakers. So when we look at the potential for vessels, do we look at nuclear-powered propulsion systems for vessels, or a marinized charging concept using nuclear fuels? Where do you think it's really going to go, and what's the most likely? And who wants to go first on that one?
Well, I can take it. So I believe there is, looking at shipping, I think that there will be a bifurcation of the market. We believe that the large, let's say, deep sea ships will have an advantage of going into, let's say, direct nuclear power, not nuclear propulsion, because we are talking about an atomic electric ship. Okay, so with a power generation and then electric propulsion. So there is no direct, let's say, mechanic connection between the power conversion system and the propellers. But there will be also a lot of vessels that will don't want to or could not go to direct nuclear power, and they will need to decide whether to use fossil fuel and pay carbon taxes, or let's say use green electric fuel. But in any case, these will be, let's say, more expensive. So we see a bifurcation of the market. For direct on-board application, we need, let's say, smaller reactor, while if we consider floating plant to produce green fuel, in principle, we need as large reactor as can be built and installed in this asset. So there is a little bit of conflicting requirements. Probably in ships, the first application will be very large ore carriers, trading always along the same route. And this will start, let's say, making the shipping industry, let's say, comfortable with the knowledge of nuclear cargo ships. Another could be, let's say, domestic land continuity ships in US on the East Coast or West Coast to Alaska and the West Coast to Hawaii. That will be probably, let's say, the first applications.
Yeah, maybe just quickly. So I think if you look at the whole transition pathways, the question to ask is where are the low-hanging fruits? First of all, where are the low-hanging fruits in technology, and who is already building what? So I guess in that sense, maybe electrification of electric vessels might be a low-hanging fruit as compared to nuclear propulsion or nuclear linked propulsion. And then you look at the regulatory barriers. So putting nuclear reactors in a barge is challenging. Regulations doesn't really exist. We're creating regulations to make sure that the ships have something to be compliant with. And then you get more challenging when you have nuclear propulsion systems, where basically these barges run around in the international water. And so there's additional layer of barriers, maybe not really a low-hanging fruit, but we probably will get there at some stage. And so if you look at these lower-hanging barriers, low-hanging fruit, slightly higher fruit, and then you look at the tips of the trees, then we might be seeing actually a gradual phased transition. But where does floating charging might go? If you have floating nuclear power plant, charge the electric vessels, so you might think that, oh, ocean electrification is just going to stop there. You have the charging vessels might go nuclear. But then the other argument is, if you can do this charging, then maybe at some stage you could also have nuclear propulsion, where you turn this nuclear propulsion into some kind of like hybrid vehicles that we run electric ships essentially, but you have a nuclear power plant on board. And you can also have additional value propositions of producing power directly from onshore facilities.
Hybrid, yeah?
Yeah.
Okay. Okay, well,
yeah. I just want to remind people that as far back as 1960, there had already been a nuclear-powered passenger ship called Savannah. And it's a cargo ship as well as passenger ship, right? It is the advantage of a nuclear-powered ship is that, you don't need a lot of room or holes to carry your fuel. It's so compact. Therefore, it increases your cargo capacity, right? And you don't have to stop to refuel for, some ships, some submarines that go on for like 6 months, a year, and the only reason they ever to come to shore is not to refuel, but to replenish the food stuff and stuff like that. So nuclear ships is certainly a good way forward.
thank you very much. Okay, I know that I could talk some more on this, but we'll have to wrap this one up. So thank you very much to Dr. Giulio, Dr. Victor, and Mr. Lim for joining us for this panel discussion, and thank you very much.
Thank you. Have a nice evening.